Think about how Newton saw gravity. That's what got us to the moon. Ever wonder if we really get time? Is what we know just the tip of the iceberg? Newton's idea wasn't just a theory, it was like a key to the universe, showing us how complex and cool it really is. So, how does Brian Cox's new theory mess with what we thought time was? What does that mean for how we see reality? Let's go digging into time itself and check out Cox's crazy new thought about what time is in space. There are secrets waiting to be found, and some have to do with time and gravity, the basics of everything. What if time wasn't normal? What if it sped up or slowed down? And what if gravity isn't what we think? That's where Einstein's theory of relativity comes in. It flips how we see time and gravity upside down. Einstein, a super smart dude, gave us a fresh way to look at the universe with his relativity theory. His work made it possible to get how time works in different situations, like when going super fast. It all started in the early 1900s when Einstein came up with two wild theories, special and general relativity. Special relativity, in 1905, changed how we see reality. Basically, it says the rules of physics are the same for everyone who isn't speeding up, no matter how they're moving. This brought up the idea of time weirdness, like time stretching or shrinking depending on the situation. A cool way to see this is with a light clock. Imagine you're on a spaceship going almost the speed of light. Inside, there's a light beam bouncing between two mirrors, going the opposite way of the ship. The speed of light is the same for everyone, so the light beam looks like it's going on a longer, angled path. The time it takes for the light to finish its trip should be the same for you in the ship and someone watching outside. But, because the light has to go farther for the person outside, it looks like it takes more time. This time difference is what Einstein called time dilation. Time slows down for the person moving compared to the person standing still. So time acts strange depending on how fast you're going. Relativity isn't just a theory. Scientists use machines like the Large Hadron Collider to make particles go super fast, close to the speed of light. When things go that fast, we have to think about time differently to get things right. Einstein's special relativity, from 1905, switched up how we understand the universe, especially when it comes to time and motion. This theory makes us rethink stuff. It says the main rules of physics are the same for everyone, no matter if they're moving or not. This is odd because we usually think adding speed makes things go faster. But Einstein's theory says nothing can go faster than light. That's the speed limit. From there, things that look like they're happening at the same time for us might not look that way for someone going nearly the speed of light. Another idea from this is length contraction, meaning things look shorter when they're moving, if you're standing still. Plus, the famous E=mc² shows how energy and mass can change into each other. This is key to understanding how small particles act when moving fast, and for things like nuclear. Special relativity isn't just a brain thing. We use it in everyday stuff like GPS. GPS satellites send signals to your device, and they're moving. Because of that, time acts a bit different for them. If we didn't fix for these time changes in GPS, your directions would be wrong. So special relativity tells us time is not the same everywhere for everything. It depends on how things are moving. This is a mind-bender. It's like saying the normal rules we use to explain the universe aren't complete. According to special relativity, time isn't set, it changes with motion. Key ideas like the speed of light staying the same and how energy and mass relate have been proven in tests. But wait, there's more. Einstein's general relativity, from 1915, looks at the deep between gravity and the universe's structure. It flipped the old idea that gravity is just a force pulling things from far away. Instead, it says gravity is from things bending space-time. It's like saying gravity isn't a mystery force, it's just how things move through the universe. According to Brian Cox's take on general relativity, this means thinking of the universe as four-dimensional, with 3 space dimensions and 1 time dimension. Big things like stars, planets, and even us change the shape of reality around us. That's what makes gravity. See spacetime like a big stretchy sheet. When something big like Earth is on it, it makes a dip. If you put something smaller like a ball near that dip, it'll roll toward it. That's how things react to gravity, not because of a mystery force, but because space-time is curved. General relativity gives a full explanation of how things move in our solar system. For example, it gets right how planets orbit the Sun. Earth's orbit around the Sun can be called out by the theory. Brian says this is way different from the old idea of gravity just setting things in motion, which had trouble explaining how planets move. The game-changing point is that space-time is curved, like a stretchy sheet, and that lines up with what we see. A big confirmation of general relativity came during a solar eclipse in 1919. Sir Arthur Eddington led a trip to watch how light from faraway stars bent as it went near the Sun. The theory said the Sun's mass should make the light curve a bit. During the eclipse, the observations checked out Einstein's predictions, giving strong proof for the theory. Just like motion can change our experience of time, according to special relativity, gravity messes with time too. In places with strong gravity, time goes slower than in places with weak gravity. So if you were near a black hole, your clock would go slower than one far from it. General relativity brings up the idea of black holes, places where gravity is so strong nothing, not even light, can get out. The line around a black hole is called the event horizon, which is the point of no return. Once something crosses that line, it's pulled into the black hole for good. Einstein's general relativity has big effects on the universe's build. At first, Einstein put a cosmological constant in his equations because he thought the universe was still. But when scientists said the universe is getting bigger, he later called that a big mistake. The idea of an expanding universe, from general relativity, is the base of the Big Bang theory, which explains where the universe came from. Another cool idea from general relativity is gravitational waves. These are ripples in spacetime made by big things moving, like when black holes or neutron stars come together. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, found gravitational waves for the first time, giving more proof of Einstein's theory. Over time, scientists have done tests to check general relativity, and it has always held up. Whether it's by studying how planets move, watching light bend, or finding gravitational waves. While some are blown away by gravity in the world of physics, it's normal to question ideas. For gravity, many scientists are checking how we think about this key force. One theory that fights traditional gravity is called modified Newtonian dynamics, MAND, which says gravity acts different at low speeds, especially in galaxies, without needing dark matter. Instead of adding unseen matter, MAND says gravity gets stronger at low speeds. The gravity story also has the ideas of dark matter and dark energy, which were brought in to explain some cosmic things. Critics say these ideas might not be needed, and other theories could explain what we see. Some scientists who turned down Einstein's theory of gravity are checking out other ideas, like unknown particles or forces that might change or upgrade our understanding of gravity. It's good to note that in science, new ideas are tested hard to see if they hold up. For example, Einstein's idea of time as the fourth dimension, where time traveling could be stopped by the speed of light, has been paired with ideas like wormholes and shortcuts in spacetime. Stephen Hawking's chronology protection conjecture says that going back in time is not likely from a physics approach. Ongoing tests are trying to see if these new theories can explain things like gravity in a way that lines up with what's known. While different theories have been checked, none have replaced the gravity principles. Questioning and testing ideas is how science moves forward. These checks make for deeper looks into the universe. As for gravity, general relativity is the most tested theory to date, explaining things like how planets move and how light bends. General relativity is strong because it's simple and can explain what's seen, like how planets orbit the Sun. Einstein's special relativity says that time acts different depending on how you're moving. Let's see how this messes with space travel. Space exploration is wild, but hard because space is huge. Also, Einstein's theory says the speed of light is as fast as anything can go. This makes space travel hard, especially when trying to get to the stars. To get what happens to time during space travel, we can think about the twin. In this thought test, one twin stays on Earth, while the other goes on a fast trip to a distant star. When the space-traveling twin comes back, they see that less time has passed for them than for their twin on Earth. This means they have gone forward in time. Time is important in space exploration because over long trips, time slows down for those going fast. If astronauts were to visit stars, where time dilation is very clear, they could age slower than those on Earth. This may seem like sci-fi. It's a real thing called out by the theory of relativity. Picture a mission to a distant star system. Because space is so big, such a trip would take years, even at high speeds. Astronauts on the spacecraft would feel time slower than those on Earth. Time change affects both people and tech. For example, GPS systems and satellites in space need to fix for time dilation to work right. Space travel also has, like cosmic radiation, mind of being alone, and the body of being stuck in a box. In our lives, we can see the effects of time dilation in GPS. These systems need exact timing from satellites that are moving. Since the satellites feel time different than us, not fixing these differences would make your directions wrong. Lastly, let's see why time seems to move in one way. Time runs our lives, moving from past to present to future. But why is time one way? That's where entropy comes in, an idea that measures how disorder rises over time. Entropy, tied to the arrow of time, tends to grow, making time go one way. The second law of thermodynamics says that in any closed system, total entropy will either rise or stay the same. Simply put, entropy only goes up and never goes down. As we see in everyday things like ice melting or coffee getting stirred,